Good morning, students. Welcome to Machine Integration live lectures. In this lecture, we'll define Dini derivatives and see some examples. So, if we recall how we define lim sup of a sequence an as n into infinity, this is defined as you find supremum of ak, k greater than or equal to n, then infimum among all n greater than or equal to 1, right? Similarly, how we have defined lim inf of an as n tending to infinity, this is infimum of ak, k greater than or equal to n, and then you take supremum over n, every natural number n greater than or equal to 1, right? Now similarly for f, if f is a real valued function, so if you take f of x, then for this also, uh, where f is defined over all x, right? Then you can talk about what is meant by this lim sup, or you can call it upper limit. Okay, upper limit as x tending to y. Okay, this you can also write as lim sup of f of x, right, as x tending to y. This how we can define. Similarly is you take supremum of f of x, okay, where mod x minus y, this one should be between 0 and delta, and infimum among all delta greater than 0, okay, right? Similarly, how we can define lower limit, and we can also define upper limit one side, that means f of x as x tending to y plus. That means what? It is x approaching near to y but from right side, that means greater than y, right? So that means this lim sup of f of x extending to y plus, you can define this as supremum of f of x, where what can we say about x minus y? This time x minus y, because x is greater than y, so it is near to y but it is bigger than y, right? So what we'll get here is supremum of x minus y is less than delta and infimum over delta greater than 0. Okay, that means it is all x belongs to y comma, so that is same as saying that x belongs to the interval y comma y plus delta. Okay, so all x we are taking greater than y but close to y, right? Similarly, you can define lower upper limit of f of x as x tending to y minus, this is same as supremum of f of x, okay, where this x minus y is bigger than minus delta and less than 0, and infimum of delta greater than 0. This is same as saying that x is in the interval y minus delta to y, okay, in this interval, right? So if you want, you write same as lim sup of f of x as x tending to y minus. Similarly, we can define the same way, we can define lower limit or lim inf of. So similarly, I will write just only one. Similarly, lower limit of f of x, okay, x tending to say y plus. How we can define this one? This is nothing but lim inf of, lower limit means lim inf of f of x, x tending to y plus. So this is same as you take infimum of f of x, right, over this x minus y is less than delta and supremum among all delta greater than 0. Okay, so all these three you can write it for lower limit also. I'll just leave it with one, right? Okay, now we know something about derivatives. Okay, so we'll recall that when we say that f is differentiable at x, if so, if f, the limit f of x plus h minus f of x upon h as h tending to 0, if this limit exists and is finite, okay, then we say that f is differentiable at x, right? And denoted by, and we denote this by, denoted by f dash of x. Okay, so if suppose limit does not exist, so this is one. If limit does not exist, then we can talk about uh, at least left hand limit, left hand derivative and right hand derivative. Okay, left derivative and right derivative. So if f dash of x does not exist, then we will find left derivative, left derivative. What is that? F dash of x minus. Okay, f dash of x minus. How it is defined as? Hmm? This is defined as limit h tending to 0, limit h tending to 0 minus f of x plus h minus f of x upon h, and right derivative, right derivative f dash of x plus, if you denote this, limit h tending to 0 plus f of x plus h minus f of x upon h. Okay, so even if these two also doesn't exist, so if these two exist and they are equal, then we say differentiable, right? If they are exist but not equal, then we say it is not differentiable, but left hand side, left derivative and right derivative exist. Third one, if this f dash of x minus and f dash of x plus does not exist, okay, then we can define using, these are all defined using limit. So then we will define using this lim sup and lim inf of the function, and we'll define four quantities called, then using lim sup and lim inf, we define uh, four quantities called, they are called Dini derivatives. Okay, Dini derivatives, or you can also call it as Dini derivatives. Okay, so that we will define now. So definition, uh, Dini derivatives of f at x are defined as, there are four different types. One is d plus of f of x. Okay, this is denoted, this we will call it as upper, okay, right, we will call it as upper right derivative. Okay, upper and then right derivative. Okay, d plus of f of x, this we will denote as, we will write here, first we will write upper right derivative, this notation d plus f of x, this is equal to limit h tending to 0 plus this upper limit, okay, not limit, upper limit. Okay, upper limit of f of x plus h minus f of x upon h. Okay, similarly this time it is lower but right derivative. Okay, lower right derivative, this we denote by d plus fx, this is lower limit of h tending to 0 plus f of x plus h minus f of x upon h, right? Similarly, what are other two? Hmm? The other two is upper left derivative, this is defined as d minus fx, this is upper limit of h tending to 0 minus, right? Or if you write it here as 0 plus, then it is f of x minus f of x minus h upon h. Okay, or if you write here h tending to 0 minus, then you write here as x, f of x plus h minus f of x upon h. Okay, and lower, the fourth one is lower left derivative, of f at x, this is denoted by d minus fx, which is equal to lower limit of h tending to 0 plus f of x minus f of x minus h upon h. Okay, these four derivatives we can define, and we can observe that. So we'll write as some remarks from this definition. We can observe that this upper and right derivative, so d plus fx, because it is supremum of this same function, and this lower right derivative is so lim sup of one. First one is lim sup, the second one is lim in. So we know lim in is always less than or equal to lim sup, so d plus of f of x is always greater than or equal to d plus this one, right? And similarly, this is d minus fx is always greater than or equal to d minus fx. Okay, right? Then the second remark one can observe that if d plus fx is equal to d, that means upper right derivative is equal to lower right derivative, then we say that this is the right derivative. Okay, this upper right derivative is equal to lower right derivative, then we say that f is right derivative. Okay, so f is right derivative if d plus f of x is equal to d plus fx. Okay, and left derivative if d minus fx is equal to d minus fx, right? And if all these four are equal, if d plus f is equal to this one is equal to d minus f is equal to d minus f, okay, of course everywhere x is there. Okay, then we say that f is differentiable at x. Okay, so if all are equal, then it is differentiable. If suppose d plus upper and left lower right derivatives are equal, then it is right derivative. Or lower and upper left derivative are equal, then it is left derivative. Okay, we'll see one example how we can calculate this. Okay, so let's talk about some example. Consider the function f of x, which is equal to x times sine 1 by x when x is not equal to 0, and 0 if x is equal to 0. Okay, we have seen that. We'll see whether it is differentiable or not, and if it is not differentiable, is it right differentiable or left differentiable, or it is not at all. Okay, then we'll calculate d plus f at 0, okay, d minus f at 0, right? Then d plus f at 0 and d minus f at 0. We'll find these four values. Okay, so it is not at all difficult. We'll try to put by definition what is d plus f of 0. This is upper limit of, okay, as h tending to 0 plus, right, f of x plus h. So your x is this 0, so f of h minus f of 0 upon h, but f of 0 is also equal to 0, so this is same as how we can write upper limit. So first we'll write one more step, upper limit of h tending to 0 plus f of h upon h, because f of 0 is 0. Okay, now if h is not equal to 0 tending to 0, so f of h is h into sine 1 by h. So therefore this is same as upper limit of h tending to 0 plus, okay, sine h and h will get cancelled, sine 1 by h, right? Now this, if you write whatever we have used this notation, upper limits, right, then what you will get here is, it is first you find supremum of this function sine 1 by h, where your h is between 0 and delta, and then find infimum on all delta greater than 0. Okay, so we want to calculate this value. So what should be guess? We want to find some suitable h such that what can be the maximum value of sine it will take. We know already sine x, so we know that sine x is between 1 and minus 1, right? So we'll see so maximum value takes 1, So question is, can we find some h such that sine of 1 by h is 1? Then this supremum value will become 1, right? Because even at 1 h, if this takes value 1, then this supremum of these values is 1. Then we will find infimum. Is this clear? So now you can check that. So let delta anything greater than 0. Now then we can apply by Archimedean property. Then by Archimedean property, there exists you can call it a natural number n such that hmm, such that this 1 by n or delta times n is greater than 1. So delta times n is greater than, so let me write that, because nx is greater than y, so delta times n is greater than 1. This is same as saying that 1 by n is less than delta. Okay, fine. Now we will take, so take h in such a way that this h is less than delta. So and also we will find sine of 1 by h. So obviously you take 1 by this 2n pi plus pi by 2. Okay, then you can check that this is less than, okay, 1 by n, right? Because this is bigger value, so it is smaller than this, which is less than delta. Okay, so your h is between here. And what can you say about sine 1 by h, which is sine 2n 2 capital N 2n pi plus pi by 2, but we know this is same as sine pi by 2, which is 1. So for this h we are getting this value as 1, right? This implies the supremum is equal to 1. This implies supremum of sine 1 by h, where h is between 0 and delta, this value is 1, because the maximum value it can take is sine is 1, right? This implies infimum of this value supremum sine 1 by h, where h is between 0 and delta, and delta anything, any delta you greater than you take, we started with any delta greater than 0, you get every time 1, so infimum of all such values is 1. Therefore d plus f at 0, this value is 1, right? Any problem? So d plus f of 0, this value is 1. Similarly, what is this lower right derivative? And d minus d plus f of 0, that means lower right derivative. This is nothing but lower limit of h tending to 0 plus this f of x plus h, so f of h minus f of 0 upon h, but this is same as lower limit of h tending to 0 plus sine 1 by h, right? But this is again is same as, because it is a lower limit, so we will find first infimum of sine 1 by h. Okay, then we will find supremum of delta greater than 0, okay, where h is between 0 and delta, right? So just like how we have seen here, in sine takes minimum value minus 1, okay, and maximum value 1. So if we can find some h such that sine of that value is minus 1, then this infimum value is minus 1, right? So same concept you can use. Take h, which is equal to uh, how we have taken here 1 by 2n pi, instead of plus pi by 2, we will take 1 by 2n pi plus 3 pi by 2, because we know sine 3 pi by 2 is minus 1, right? Then again h is less than delta, right? And this sine 1 by h is equal to sine 2n pi plus 3 pi by 2, but which is same as sine 3 pi by 2, so this value is minus 1, right? So for every delta greater than 0, this implies infimum of sine 1 by h, okay, where h less than delta, is value is minus 1. Then when you take even supremum over that, so supremum of delta greater than 0, infimum of sine 1 by h, where h is less than delta, this value is also minus 1. This shows that d plus f of 0 is equal to minus 1, right? So lower right limit, okay, is lower right derivative is minus 1, okay, and upper right derivative is 1. So it is, this function is not even right differentiable, right? Similarly, what can you say about quickly we will find that, what can you say about d minus f of 0, right? It is d minus f of 0. This is upper limit of h tending to, sorry, upper limit of h tending to 0 plus f of x, that means f of x is 0 minus f of h upon h, right? Fine. Now this is, if you simplify this, this is same as f of h. um, Here you will have f of x minus h, so it is minus h here, right? So if you have f of minus h, that is in place of x, if you substitute minus h upon sine 1 by minus h, so minus minus will get cancelled. Yeah, so this is same as upper limit of h tending to 0 plus f of 0 is 0, then here you will have minus f of minus h. So uh, okay, so this is f of minus h upon h, right? This is same as because it is upper limit, therefore this is same as infimum of delta greater than 0, supremum of 0, h is between h and delta. Now we will find what is minus of f of minus h. So here minus is there, right? Then f of minus h, so you can write minus 1 by h. What is f of minus f of minus h value is minus h into sine 1 by minus h, right? So therefore minus minus will get cancelled, h will get cancelled. Then uh, this infimum of supremum, what we'll have here is this is minus sine 1 by h. Okay, this is you will have, right? So this is nothing but this infimum of supremum, that means lim sup of this one is, when you have minus, this is same as minus of this supremum of infimum of sine 1 by h. But this we have already calculated, this value is what, supremum of infimum of h is this supremum, here uh, it is, so supremum of infimum of h, this value is minus 1, right? So if you supremum of infimum minus, this is minus 1, and you have minus here, so this value is 1, right? So therefore minus of this we have already seen, that means it is minus of this means d minus f of 0 is equal to 1, right? So similarly you can calculate, so similarly we can find d minus f of 0, this is minus 1. So I'll leave it as exercise to show that this is this one. Okay, so basically what we are seeing, because of this minus, okay, this lim sup will become lim in. Okay, right? Oh, now let's write some more exercise. You can try, because this problems asked many times in exam also, so you can find out, and if you are not finding, you can ask me, I'll explain in next class. So what are those values? Suppose take f of x is equal to x into sine 1 by x if x is greater than 0, and 0 if x is equal to 0, and the other one is x times sine 1 by x plus 3x if x is less than 0. So it is similar to the problem, but earlier here x is not equal to 0 0, but if x is greater than 0 this value, and x is less than 0 this one. Okay, so try to find all find Dini derivatives. Okay, Dini derivatives. And second one, so these are all asked in either net or set some problems, so you can work out really. Okay, net or set. Then second one, if you take f of x, you define as mod x, that is x if x is greater than or equal to 0, and minus x, x less than 0. Okay, in this case also fine. Here you find linear derivatives at x is equal to 0, because the problem is only at x is equal to 0. Similarly here find linear derivatives at x is equal to 0, right? And the third one is f of x is equal to mod x if x is a rational number, and 2 times mod x if x is irrational number. Okay, then find or show that I'll also give this d plus f at 0 is 2, and d plus f at 0 is 1, and d minus f at 0 is minus 1 and d minus f at 0 is minus 2. Okay, and if you have any difficulties you can definitely ask next class, and if you are having any difficulty we'll solve these problems and we'll go further. Okay, so we'll stop here and we'll see next class how these Dini derivatives will be used in finding differentiation of monotone functions. Okay.